Good evening. All right, we've got a good crowd here, and welcome to you online as well. I'm Megan Clifford, the Associate Laboratory Director for Science and Technology Partnerships and Outreach, and it's a pleasure to be here with you this evening. I am welcoming you to our OutLoud public lecture series that is entitled Community and Climate, Responding to Our Warming World. This OutLoud lecture series is one way that Argonne shares our fascinating work with you, the science-curious community. Our lectures highlight Argonne's cutting-edge research and pivotal discoveries that meet some of the world's most complex challenges. Tonight, leading environmental scientists and community leaders will discuss their collaborative research addressing the negative impacts of climate change. Now, I have the pleasure of introducing our laboratory director, Paul Kearns. Paul has served as lab director since 2017, and during that time, he has set the laboratory's strategic vision to deliver pivotal discoveries, pioneering leadership, and powerful scientific tools and facilities. We are delighted to have him here tonight to kick us off. So please help me welcome to the stage Argonne Director Paul Kearns.
Thank you very much, Megan. It's indeed a treat to be here. I'm really impressed, encouraged, and feel a great deal of love for the laboratory with all of you here and those of you online as well. So thank you for embracing the laboratory as a part of the community and also for really coming to learn about our science. We're really pleased you're here. I am Paul Kearns. I have the distinct honor and privilege really of serving as the director of Argonne National Laboratory. It's a wonderful place, really fantastic in terms of the facilities, scientific facilities we have, but really it's, as I often say, our people are everything, and really they make the difference in terms of the great science and the great work we do here at the lab. So pleased we've got many of the Argonne employees in the audience tonight as well. It certainly is a pleasure to host this program both in person and virtually, and I'm happy that we can share, as Megan said, our cutting-edge research and our pivotal discoveries with a wide audience. As many of you know, Argonne has a prominent history of developing clean energy, promoting sustainability, and advancing climate change. More than 75 years ago, Argonne was founded to harness the power of nuclear reactions for peaceful energy purposes. Since then, we've expanded to building clean energy technologies for a more sustainable and energy-efficient future. Our current research includes modernizing and securing the nation's electric grid, developing next-generation batteries that are safer and have higher energy densities, and creating high-resolution climate models which provide policymakers with actionable data, actionable information, really, to mitigate and adapt to the changes in climate that we're all experiencing. All of which can help communities and industry make better, more informed decisions on clean energy transitions. This work is needed now more than ever. It's critical to mitigating the negative impacts of climate change. That's why I'm pleased to see our scientists and communities work together through our Urban Integrated Field Laboratory, which is called the Community Research on Climate and Urban Science, or CROCUS. Focusing on the Chicago region, this exciting initiative is transforming how we do collaborative, community-scaled climate research. The CROCUS team consists of scientists and academic and community partners who are working together alongside the Department of Energy. This team is gaining the necessary insights and understanding to effectively address climate change in urban environments across the Chicago metro area. Our research will help these communities build resiliency in a warming world. Our advancements in infrastructure, sustainability, and energy efficiency will also contribute to more communities, more opportunities, and better neighborhoods for all. This is important not just for our region, but for the country as a whole. Really, the country that advances climate solutions will certainly lead the 21st century. Jobs, economic growth, and a brighter tomorrow for everyone depend on it. Now, I'm happy to introduce our moderator for this evening, Robyn Wheeler Grange. Robyn is the Director of the Office of Community Engagement here at the laboratory. In this role, she and her team lead the laboratory in establishing and building relationships and strategic partnerships. Her outreach broadens and deepens the impact of our science and technology in local and regional communities. It makes us more relevant. So please welcome Robyn to the stage, please. Thank you very much.
Well, thank you, Paul, and good evening to everyone. Tonight, we're going to take a look at the novel and important research being done by CROCUS and the CROCUS research team as they work to understand the impacts of climate change in urban environments. But before we start our discussion, permit me to set the stage. Early studies on the impacts of climate change have been on a global and regional scale for the most part. But according to the United Nations, more than half of the global population lives in urban areas, with projections of an increase to about 2/3 by 2050. So we must understand climate change in urban settings in order to intervene and mitigate its negative impacts for a large part of the global population. As a result, in recent years, cities have become increasingly recognized as key sites for climate research. Now, while scientists have some knowledge about climate change impacts in cities, it is usually related to a city as a whole and does not allow us to understand the difference in these impacts at a local level. The CROCUS research team is taking the novel approach of observing climate change and its impacts on scales at a granular level, as small as a neighborhood or even a city block, to account for and understand the multiple factors that affect the interactions between urban systems and climate. Doing this research with Chicago as the field laboratory presents an urban ecosystem ripe for in-depth study. Chicago has the Great Lakes coastline, a complex water system, varied atmospheric and climate conditions, industrial impacts, and significant environmental justice issues. All of this has a cause and an effect that we want to understand. CROCUS is also novel in its approach to community engagement. To advance our research, we must work collectively with some of the communities most affected by climate change. Learning the current and historical climate impacts on communities and the community's priorities for the future directly informs our research and requires understanding of the lived experiences of the residents. Our community partners have been part of the research team from the start, which is unusual. And they've been working alongside the scientists, contributing to the science questions and the research activity. Through this partnership, communities will be able to implement data-informed, community-based solutions that will make their neighborhoods more climate resilient. CROCUS's communities of focus include Chatham, Woodlawn, Humboldt Park, and the Chicagoland region, which is represented by the Metropolitan Mayor's Caucus. So now, I'd like to turn your attention to one of our communities of focus, just to give you a sense of the kind of approach we're taking. The community we're going to focus on in this video is Chatham.
Chatham has a long history of flooding. Every couple of years in our single-family Georgian house, our basement would flood. 2 occasions, our house caught on fire because of the electrical, and one was so severe we had to move out, and it took 6 months for them to completely renovate the house because of all the smoke damage that had occurred. I don't have a single thing from my childhood because it all got wrecked, burned, smoked, and it hurts because you don't have that wonderful nostalgia that you can touch and feel. And our community was residentially mature in the 1920s, and they only heated one room. The living room is heated or cooled, and the bedrooms are not. So when you have these really horrific air quality events, residents that live in apartment buildings, they want relief on a summer day, they open the window. But if it's a hot air, poor air quality day, it is very suboptimal for them. And so when CROCUS approached us in being their community partner, interested in making climate change less of an issue in the Chatham community, we said would love to do it because, as the CROCUS scientist said, it rains all over Chicago, but it floods in Chatham. So fix the flooding in Chatham. Equity looks like when the decisions are driven by the community, for the community. We're telling you what's good for us, and then we're working collaboratively to address the issue. I find that when we talk from a scientific lens, not based on please help us, but we have the science that can inform that if you change where that sewer pipe is and move it a mile, 50% of the basements will flood less. That is something that is tangible. That is what I'm really hoping that CROCUS can help us make informed decisions because we have limited resources. We don't want to guess. We want to know.
Powerful video, isn't it? Right? Gives you a sense of what we're trying to do with CROCUS. The climate challenges the CROCUS community faces, as described by Nidra Sims-Fears, illustrate the CROCUS research focus. Now, Nidra's going to join us for our discussion a little later in the program, but at this time, I would like to welcome our panelists to the stage. If you would please hold your applause until the panelists have taken their seats, that would be wonderful. Our first panelist is Max Berkelhammer, CROCUS lead principal investigator from the University of Illinois, Chicago. Next is Ralph Cintron, who represents the Humboldt Park community, serving as the co-chair of the Environmental Committee for the Puerto Rican Agenda, which is one of our community partners. Next to join the panel is Scott Collis, CROCUS measurement lead from Argonne National Laboratory. And finally, Raul Cortamorthy, who is CROCUS's deputy project director from Argonne National Lab. Will you please join me in welcoming our panel? I'm really excited to moderate this discussion. The Office of Community Engagement is supporting CROCUS in its community engagement work. So the whole team is here, and we're excited to hear from you all. Max, I'd like to start with you. Am I right about that? Yes, okay. Earlier, I mentioned that climate change research has primarily been focused at a global and a regional scale. What does climate change look like more locally?
Sounds good. Thanks, Robyn, and thanks everyone for coming. It's nice to see everyone here. At 3:45 today, I was in front of a classroom of 5-year-olds. So this is a really welcome sight, I have to say. Everyone's sitting down, listening, not running around. It's great. So I'll draw your attention to the slides up above. We're going to jump right into some data here. If you look at the map on the left here, you can think of that as a thermal image of the picture of Chicago taken from one of NASA's satellites called the GOES 16 satellite. And what you'll see in that image quite clearly is that Chicago, like all cities, are significantly warmer than the areas surrounding them. And we've known this for a while. We've known this for over almost 200 years based on early meteorological experiments in London that cities are hotter. And that's a phenomenon I think a number of you may have heard of called the urban heat island effect. And if you now focus your attention to the map on the right, this is a similar image. This is a thermal image zoomed in on one particular neighborhood in Chicago. It's the Humboldt Park neighborhood. It's one of our communities of focus as part of the CROCUS project. And this is also from a NASA satellite called the EcoStress satellite that is on board the International Space Station. And it allows really detailed look at temperatures at the surface of the Earth. And what we've done here is we've averaged surface temperatures for each block in the neighborhood of Humboldt Park. The bright reds being warm, the kind of oranges being cooler. And when you zoom in, you start to see a very different picture. The urban heat island is not really an island. It's not a monolith of heat in the city, but it varies significantly between neighborhoods, even within neighborhoods, and even to the scale of blocks can be warmer than other blocks. So the experience of a heat wave, for example, will depend on where you live, where you work in the city. So as a climate scientist, I'm really interested in what drives these gradients, in this case in Humboldt Park, a 3-degree gradient. That's quite large between the eastern and western side. Just a 2-mile difference across this neighborhood. It's a small area. Why is there this temperature gradient? How is that going to be exacerbated in a warming climate? To understand what that means to the communities living in Humboldt Park and what this temperature gradient reflects onto the community, I'm going to pass it over to my colleague, Ralph.
Thank you, Max. If you take a look at the maps up here, one of the things that you will notice is that the right-hand side, this side over here, is more of a white population, higher income levels as well. I hope you can read the maps. I'm not too sure. But if you can zero in on the maps, that's the data that it's telling you. Now, this is the Humboldt Park area. It's that little blue chunk is the Humboldt Park itself. To the east of Humboldt Park are a set of processes which have been occurring over 3 to 4 decades. Now, in the Puerto Rican Agenda, which is the activist organization that I work with, we call that story gentrification. In other words, coming from the east, more money is coming, and it's pushing people to the other side of the west of Humboldt Park. So there are concentrations of Latinos. These would be mostly Puerto Rican. They could be Mexican. They could be a variety of Latino populations there. But what has been happening over, like I said, over 3 or 4 decades is the Latino population was at one point east of Humboldt Park, and it is no longer there. So we might try to understand, how does that occur? Well, it occurs because you have low property values, you have vulnerable renters, and at one point or another, a developer sees the opportunity to make money, and then slowly but surely the area starts to gentrify. So that's what has happened, and we're working with these 2 indicators for now, that of household income and Latino populations versus white populations and so on and so on. We're not so sure yet. Max and I have been working on these kinds of maps, seeing if we can create correlations between things like tree canopies and heat and so on. But at the stage that we're at right now, that seems to be the story that's unfolding. So I'll turn it over back to Max.
All right. Thanks, Ralph. So if you take the kind of community perspective that Ralph provided and look back at the temperature map, what you see is as the community, the Puerto Rican community, for example, has been displaced from the eastern to the western portions of Humboldt Park, they're also being displaced into warmer and warmer areas. So there's a climate consequence or a climate exposure consequence to this displacement or gentrification process. And again, this is not a trivial temperature gradient that we're talking about. 3 degrees is quite significant difference. That's shown in the figure on the left here, again, indicating this westward displacement and the higher temperatures there. Now, the last map I want to point to before we leave is another satellite-derived image, but this is of canopy cover. So this is block level percentage of of that area that's covered by a tree canopy. And again, you'll start to see a similar gradient. On the eastern side of Humboldt Park, it's very treed, it's very green. And on the western side of Humboldt Park, it's very exposed. There's very few trees covered there. There's 2 points I'd like you to take away from this. The first is there's a strong correlation between temperature and canopy cover. These green areas are cooler than the exposed areas. So there's a causal relationship between the cooling effect of the canopy and the temperatures experienced. The second is, again, as these communities are displaced, they're not only displaced into warmer areas, but less green areas. And there's a lot of health consequences to losing the canopy. It has a lot of positive health benefits that are lost in this process. So I'm going to wrap up here. I want to make one point. I don't want to shoot myself in the foot because I really do love satellite data, and it's one of my bread and butters. But it takes a picture of the top of the city, the top of the trees, the roofs. Very few people live in the tops of trees. Most people are spending their time on the sidewalk. That's not really seen from the satellite. And I want to make this point because you're going to hear of some of the ways that we're trying to bridge that gap between what we're seeing at the top and what people are actually experiencing in the city. So
much, Max and Ralph. It's clear that there are many factors to take into account when you're looking at climate change and how it's affecting the way that we actually feel temperature. So to build on Max's point, Scott, how do you measure, or how do we measure in ways that develop greater understanding?
Thanks, Robyn. And I do want to reiterate a point you're going to hear again and again today, which is we're going into Chicago, we are measuring, we are simulating to understand the impact that climate change will have on the communities of Chicago, and also to understand the impact the city of Chicago will have on the climate, on the collar counties and the metropolitan area, on the region, and on the globe as well. Because you see, when we simulate the climate, when we use these climate models to understand what is in Earth's future in a warming globe, the kind of data it produces is kind of like the picture the digital camera in your phone takes. When you kind of get in and you zoom in on that picture of a tree or this wonderful audience here, you get down to individual pixels. And the color for us of those pixels are the climate important parameters. They are temperature, humidity, cloud cover, rainfall. But here's the kicker. The size of those pixels are about 50 by 50 miles. So Max has been talking about trees and canopies and things like that. I can take the whole city of Chicago and plump, put it in the middle of that pixel. So to measure and to get an understanding of how climate change is affecting Chicago, we're going into that pixel. We are going into the urban canyons. We're going into the parks. We're going into our communities with sensor platforms like the ones you saw in the room next door, put together by the team up there at the back, to actually get in and measure. When you have that climate model saying it's going to be a 40-degree day, it's not going to be a 40-degree day. Sorry, I work in Celsius, by the way. I refuse to conform. If it's going to be a 40-degree day, let's say, what's that, 95, 100 across Chicago, it's not going to be the same temperature everywhere. You could see that from the maps that Max was showing. We know that when it rains in Chicago, the places where it rains the heaviest are not the places that flood the worst. Our system in Chicago is a man-made system, and it moves water. So we need to get in there to link inputs like rainfall to impacts like flooding. And so what we also do is we measure the impact of interventions. When someone puts in a new park or plants new trees, we go in there with our instruments and we measure the change that happens. We try and understand the underlying physics of how climate and the city interacts. We take that new knowledge, we put it into the models that Rao is going to talk about next, and then we can look 5, 10, 15 years out in the future and see the difference a greener Chicago, putting white roofs across Chicago, can make. And using those simulations and using this data, we can develop an in-depth knowledge about Chicago and the climate, we can take this knowledge and then work with our community partners to give them and empower them with the data they need to advocate for data-driven solutions so that a more resilient Chicago is an environmentally just, resilient Chicago, where the people that are in the wealthier, more served suburbs are not more resilient, and the people in the less well-served suburbs, zip codes, are less resilient.
That is powerful. You know, the climate change is really the great equalizer. That's what I'm hearing, right? That we're all going to feel the effects of it. And so it's really important to be able to measure what's going on now, but also measure where we're going, right? And that's where ROW comes in. ROW. Scott just mentioned the word modeling, and he described it as something that's a critical component of understanding climate change now and projecting its future impacts on the world. So what exactly is modeling, right? And how, aided by supercomputers here at Argonne, are models used to develop greater understanding to support decision-making?
Yep. So I'm going to try a different way of describing a model. I haven't tried this before, so you are my experiment. So when you think of a model, the one thing that comes to my mind is a model train set. We all played with a model train set of various, like you can buy one for $20, you can buy one for $1 million. So these are all have different levels of sophistication. They all can switch gauge, and they can all kind of go around. So you know that they all work, but they all work at different levels. So this is what I would call an analog model. You have a real railway system, and this is a model of the railway system, but it's an analog version of that works at various levels. Now, you have also probably played with something kind of like a flight simulator on a PC. That's one of the most popular games. So you can actually do a real flight simulation, like you can fly from New York to Chicago, wherever you want, and there are all this set of things you can do, what a pilot would do, and you're kind of playing with the thing. That's a digital model it's a digital version of a real flight that you have in your computer. So these are the kinds of, what we mean by a model is this digital version. So the digital version where you have the reality represented in a computer, and by representing the reality in a computer, one of the things you do, just like a flight in a flight simulator, where the airplane goes is described by physics. It doesn't go randomly wherever it wants. It's actually following physics. Something is solving an equation of how the things moves in the space. Similarly, when you think about a Earth system model, which is what we are talking about here, there are a whole bunch of systems that work together. There's atmosphere, there is ocean, there is land, there are trees. Some of this can be described by physics, like how the atmosphere, air moves from place to place. I have a physical understanding of that. I can write an equation. I can write an equation of how the ocean water is moving. I can write an equation of how the land how the water goes through the land and how the porosity of the land is. I don't know so much about the biology. Now, in the trees, kind of. Somebody like Max goes and measures things and says, if I put water, this tree will go by 2 feet. I write an equation that kind of says that. That is, we call an empirical model. So it's kind of an approximation of the process because I don't understand the physics. A climate model is a collection of all these things, some which have a solid understanding of physics, some things which we are kind of approximating. So all these systems together make a Earth system model. So you can have an Earth system model on a global scale. You can have an Earth system model on a local scale, like an urban system. In an urban system, I'm more worried about where the people are walking, where the people are living, where are the buildings, what is the color of the roof of the building, is there a solar panel on the roof of the building, where are the trees? So I'm actually looking at a very highly detailed, almost at a block scale description of the system, rather than like where is the ocean, where is the atmosphere, which is a much bigger problem. So that's what we are doing in the Chicago neighborhoods, is that we are trying to come down to a block. Our focus is on what is happening at a guy or a girl walking at 2 meters. That is a 2-meter person walking on the road. What is happening to that person? That is very hard to do because there are buildings surrounding you, there are trees and all that, and you have to look through them. Even in a modeling sense, you have to actually telescope down to that person. So that's the kind of models we are developing. And it is possible that we do it at Argonne mainly because we have these massive computers. The computer that we are getting at Argonne, next called Aurora, is right now ranked #2 in the world. It's only half operational. The next second half is coming up in a few months. Once it comes, it will be twice the fastest computer in this world. So you are all lucky that you're living next to one of the biggest computers in this world, the fastest computers. You can tell your neighbors. So why are we? What this new computer gives us? So the way we do traditional modeling is kind of you solve this equation I told you. These new computers make it possible to do something we all heard of a lot right now called artificial intelligence. Can I build a model that uses artificial intelligence to simulate this urban neighborhood at a very high resolution such that you can do in a very, why do you want to do that? When you do an AI model, it runs about 1,000 times faster than a traditional model. So I can do lots of things. If I have a really fast model, I can give it to Chatham neighborhood and let's say, play thousands of scenarios, put a tree here, remove a tree there, put a building there, put a solar roof, put a green roof. They can play all these kinds of scenario situations as we go forward. So that's the power of the new computer coming here, and that's the power of the future science in modeling that is going to change the way we live. I'm a complete believer in artificial intelligence and machine learning and how it will change we think about the future. And that's a possibility we see with this. This computer can train very large models, very, very large. Like ChatGPT, for example, is a very large language model. The kind of models we'll be developing here would be probably bigger than the ChatGPT type of model. So that's the power we are looking here. And we are very excited what we can do with that model and how it will influence a lot of the things, just not in this neighborhood, but all over the world.
Thank you so much, Raul. You can see that with each of the scientists, the importance of having community be involved, right? To help the scientists be able to develop the questions that are going to give us some real data that will help develop some powerful solutions. So we're going to hear from our community and some of our community partners in a moment, but they're very, very important to this work. Now, Scott, your measurement team has begun to collect atmospheric data from a few sites around Chicago. What's your early data? What are some of the observations?
Yeah, we deployed our first flight to Northern Illinois University back in May, and we got a real surprise from this. So for those of you who saw the display next door, you saw you had the waggle node in the middle, and then you had some of the instruments on the side. One of the instruments we had there, it measures information about air quality. It measures some of the gases in the air, and it measures this thing called particulate matter. These tiny little particles that are so small, they're suspended in the air. They're about 1/1,000,000th of a meter in diameter, and they have huge repercussions for human health. A healthy level of particulate matter is about 35 micrograms per cubic meter of air. And I thought we're going to put these instruments out around Chicago and we're going to see the impact industry has, vehicular travel has, so on and so forth. Smelting plants down in Indiana have. The worst air quality we saw, and some of the worst air quality on record ever in Chicago, occurred this year. It occurred in June and July due to the Canadian wildfires. So remember, I used that number, 35 micrograms per cubic meter. We saw 250 up to 300 micrograms per cubic meter. So it goes back to exactly you saw in the video that Nidra was saying. EPA says, go home, close your windows. That's not very good advice, or very unequal advice for those without air conditioning, or those people who need to work and are going to get fired if they go home. So I can draw a direct line between resiliency and climate change here, because we know in a warming climate, the models that Rao has been talking about, you can draw a straight line between increased number of wildfires and climate change. So I was surprised because I expected to see industry. We saw Canada, and it wasn't a good look.
I know that for you, Max, you talked about measurements as well, specifically at the ground level. And so I wondered if you would share with us what you're observing at the ground level, and what is it telling us about climate change?
Yeah, thanks, Robyn. So in my research, I tend to have I consider myself an ecohydrologist, which means I tend to look at the relationship between plants and water. And so one of the emphasis we're having is thinking about particularly the role of plants and canopies in addressing issues of flooding and addressing issues of heat in the city. So one type of instrument, we measure how much moisture is in the soil. We also use specialized instruments that measure the rate that water is moving through plants, which can tell us basically exactly how much water a plant is being used. Why this is important? If you're looking to reduce flooding, plants can lower the groundwater table and basically add a more absorptive feature. When plants move water, they also evaporate that water, which has a cooling effect. So that's one of our emphasis, really trying to get a handle on kind of what trees can provide in terms of services to the communities.
Wonderful. So, Ralph, how are these models, all of this data, right, is coming your way, and you're then able to create the different scenarios that you described. How are the models being used to tell us how to create communities that are more resilient and sustainable 5, 10, 20 years down the road?
Yeah. So one of the interesting things about climate change is that you have to depend on models. There is no way to know what is happening in the future. We don't have a second place where we can do an experiment and say, this is going to happen here and come back and fix this place. So this is the only place we have. And the way we forecast the future is using climate models. So when you're looking at this highly localized scale, at the scale of the neighborhood, the interesting thing is you don't want to just know how things are changing. You also want to know how I can improve my life or how I can mitigate this. That is a positive action we want to take. How can I fix this problem? That is within our hands. On a global scale, climate is changing. What can you do? A lot of it has to be done by government, like COP28, where Paul is going next. There's an international effort on reducing carbon at a grand global scale that is necessary. Even you can buy an electric car. If somebody doesn't find something that powers your electric car wherever you stop, it's not going to be very useful. So it has to be a government action, a large-scale action. But at local scale, we can do some adaptive actions in terms of resilience we can build into our communities that will help going forward. So how can you do that? So these kinds of models we are developing would include all these resiliency actions. What kind of roofing should we use? Can a white roof be sufficient for my neighbor, for my house, instead of putting a solar roof, which is much more expensive? What is a reasonable approach for me to cool my house? Can I put trees in front of my house? If I put too many trees, will it increase the moisture in this neighborhood and actually I start feeling more warm? So how many trees is an optimal number of trees here? Is a lawn useful? Is a lawn a waste of water and waste of resources? All these kinds of decisions. Is an air conditioning? How often do you want to switch air conditioning? These are all decisions that we make on our own. We don't ask the government to tell us when should I switch the air conditioning on, for example. So these are the decisions we are making at community scale, at our local scale, at our individual scale. So the kind of models we are developing actually will be fast enough, include all these aspects, so that the community can exercise these models, define different actions for their neighborhood, and then go to a policymaker and say, here is a scenario for my neighborhood, and this seems like the likely thing that will help us. Like just now we heard, Chatham neighborhood, maybe the sump should be 2 miles closer to me, not 5 miles away from my neighborhood. That is one of the problems for Chatham neighborhood, right? So can these things be in a scientific way? We can explain pluses and minuses, and help of a models, a numerical model that is solid, we verified with the data that we are collecting, and then give the opportunity to the neighborhoods, essentially empower the neighborhood that they can start looking at these things. So that is the power of ultimately where we want to go. We call it a digital twin at some sort, but that's kind of the vision we have.
Okay, so Ralph, you have the unique, you and Woodlawn and Chatham and the greater metropolitan area have this unique opportunity to have all of this data to help make your community more resilient. So I'm going to give you the last word for this part of our discussion. What does a sustainable, climate resilient future look like for a community like yours in Humboldt Park?
Well, that's certainly a discussion that we've been having within the Puerto Rican agenda, the leadership of the Puerto Rican community there in Humboldt Park. And there are many solutions which have started to emerge. There has certainly been a very, very strong interest, for instance, in urban agriculture. And interestingly enough, we have been thinking a lot about putting up greenhouses on tops of roofs, which will have consequences in terms of how is heat absorbed into buildings and so on. But I think the most important thing about the urban agriculture part is that it will have some consequences to create locally grown vegetables that nourishing to the community that the community itself is familiar with, and so on and so on. So that's one initiative. Certainly another initiative it has been about the curriculum and how that might lead to workforce development. So there's a major group inside CROCUS that's working on education and workforce development. And so from the perspective of Humboldt Park, when we're talking about deploying sensors, for instance, perhaps in the park itself, the discussions that have emerged there is there a way to take that information coming from the park, from the soil, from the trees, and so on, is there a way to have that information funneled over into the classroom? So we have two significant schools in Humboldt Park, Roberto Clemente High School and Albizu Campos High School. Albizu Campos High School is known as an alternative high school. But these two schools, frankly, have had historical struggles. And one of the things that we certainly are looking forward to is how do we create an incredibly novel kind of curriculum that is in no other part of Chicago, is not in the Chicago public school system, but how can we create a very novel curriculum in two high schools which have been historically marginalized? That would be a remarkable kind of thing. So anyway, I would say between those two issues, urban agriculture, which we would also like to be working with students also in that field, but also the technical side of things with solar panel technicians and so on and so on. So those kinds of discussions have been ranging across those domains.
Thank you so much. Thank you for your participation in this critical conversation. Now, we've reached the point in our evening where we're going to open the floor up to have you ask questions, both our in-person audience and our virtual audience. But before we do, permit me to recognize two additional CROCUS community partners who have joined us this evening, Edith Macra and Nidra Sims-Fears. Would you please come to the microphone and introduce yourselves?
Good evening, everyone. Am I live here on the microphone? Great. It's really a delight to be here, and I'm so excited to see so many people who are here to learn about the CROCUS project. My name is Edith Macra, and I'm the Environment Director for the Metropolitan Mayor's Caucus. We're a not-for-profit regional council of governments, and we have 275 municipal members serving 8.6 million residents across the Chicago region. So while we're a community partner, we're an aggregate of communities, and the reason that we're so vested in CROCUS and so appreciative of the opportunity to partner is that we created a climate action plan for the Chicago region. We've been in sustainability, working collaboratively across the region with a sustainability pledge that has 157 municipalities cooperating. But in 2017, we realized that we needed to step up our climate game. and be more responsive. And so in 2021, with cooperation from NOAA, and we had cooperation and assistance from Dr. Kota Marthi, working with us to create a climate action plan unique for the Chicago metro region. It's only the third regional climate action plan in the United States. So we have this plan. The plan addresses climate mitigation, or how we reduce greenhouse gas emissions. It looks at climate adaptation and resilience, and it is rooted in equity because we have a great diversity of communities across our region. We have activated mayors and municipal leaders. We need help in implementing the plan. And so that's the real value to us in CROCUS, is looking at how we translate those actions in our climate action plan, which are uniquely focused on the municipal strengths and authorities. And we know how to do the policy levers. We need the partnership of the CROCUS team on science.
Thank you so much. Nidra.
Good evening. So you saw me already on video. And so I'm Nidra Sims-Fears, the Executive Director of the Greater Chatham Initiative. And we're really excited about the CROCUS. Every time I hear the scientists, I get more excited because Chatham, our community, we represent 4 communities that in Chicago, on the heart of the South Side, 117,000 people, 44,000 households, and when you look at our community, we really are 2 communities living side by side. 95% Black, but 45% of our community members are homeowners, and their average income is about $85,000. And then 65% of our community are renters that live in 3-story walk-ups, those 1920 buildings, and their average income is $25,000. And they live in vintage units. Vintage. And so for the CROCUS data, why we are so happy about that information, just the ability to go block by block and to look at making sure that we're addressing our 2 populations that live side by side, because we want to make sure that we can advocate for the least of these in our community, and those are our renters. And so I really appreciate the chance and the continued partnership and working together. Thank you. And thank you for coming.
Edith and Nidra, thank you so much for joining us and for your contribution and your commitment to advancing urban climate science one community at a time. We really appreciate you, as we do Ralph. Now the floor, this is the moment you've all been waiting for. The floor is open for the audience to participate. So for the in-person audience, we're going to ask, we have one mic stand, we're going to ask you to use that microphone to ask your questions. And then if you have a question online, we're going to ask you to, we'll ask my colleague Renee to read the question on behalf of those who are online. If you're not able to get up, or you're just like, I'm tired, I don't feel like walking to the mic, we do have a mic runner who can come to you as well, so just raise your hand. So let's get started. Anybody to the mic, or is there, you have a question? Whoop, did I see a hand? No? Okay. You have a question. And Renee, do we have a question online? Awesome.
Thank you all, and thank you to the CROCUS team. This is very wonderful. I'm a technical person. I can understand all the data points and everything. But for a layman, how do you educate them, So they cannot get all the details and all. That is first question. And the second question is, we all went through the pandemic. We know how hell it is. But during that time, the entire world became standstill. Almost nothing happened for 2 weeks at least, 2 to 3 weeks. Do you all have any data points that determines, whether that during that time the climate change, the parameters, whatever, drastically reduced? That is one thing you need to understand. The third one is, are we doing a patch management for the underlying problem? For example, during pandemic, if the data point says that because of the emissions, whatever cars coming in, my son wrote, what is your climate change? He wrote on the paper, all the emissions coming from cars, heat, that is causing the climate change. If that is the data pointer, if the pandemic data pointers are available, then why can't the government say one word? This is because of this, we are doing this, don't do the patch management,
Well, that was a lot of questions. Who wants to take a stab at that? Raul, go ahead.
During COVID, nothing happened. It was basically no big signal, mainly because carbon dioxide has a lifetime into hundreds of years. Just stopping carbon dioxide today is not going to change anything for tomorrow. So it's not even relevant. As far as your third question, I'm wondering,
Patching up, like
so it's
small change.
small changes. So you have to think about this in a more global sense. So about 19% of the total emissions globally are from transportation sector. 30% are from energy sector. There's 20% is from industries, like steel and cement and all that kind of stuff. And the rest is mostly agriculture and buildings and things like that. So when people are thinking about carbon management on a global scale, they are looking at all these things in a very cohesive manner. It's not like they're going to hit. You see mostly cars, because what we are seeing is that one of the things we want to change all these sectors is that it will change the way we live. It is a complete life. We are thinking of living in a different way. So cars are the ones that people focus on because that's the first thing they are changing in their life is from going from gasoline cars to electric cars. So we are all focused on electric cars. But that's only 19% of the solution. The bigger solution that Argonne works on is how can I degasify the industrial sector? How can we not use carbon dioxide for making steel, for making cement? Those have huge effects. How can I use wind and solar energy instead of coal for producing power? Those have huge effects. So that's those kinds of things we worry about. Maybe the common man on the street, maybe they don't care, but it's the thing that we think about.
Thank you. Hopefully that gives you a good sense of, okay, good. Renee, would you give us our first online question for the night?
Sure. We have a question from Grant in Michigan who asks, how rapidly is the planet changing and what is climate change? Also 2 questions.
Okay. Scott, you take that one.
The planet, when you look at climate change, it's almost like listening to a song. You've got the long-term beat right there, and you can see that in rising temperatures, rising sea levels, like that's the large-scale thing. But what we're really starting to see recently, and climate models predicted this, they're climate models, and what Raul's been talking about is a testament to the scientific ingenuity of the planet, because our models were right. Because one thing they predicted, for every degree of warming, you'll see increasing extremes. So you increase the planet by a degree, you'll see not only increasing heat waves and wildfires, sometimes you see increasing cold outbreaks and cold snaps. And that's because the Earth's weather kind of sits and goes around the globe almost like on a guitar string. And as you plug more and more energy into that system, that gets more and more wavy. So you get more hot systems and more cold systems coming up and down. So what we're really seeing now that we're hitting this, 1.5, 1.7 degree Celsius, by the way, increase in global temperatures, we're seeing those extremes coming into play. So the kind of 2-part answer there, we're seeing that gradual rise. What we've really seen in the last 10 years as we go from looking at climate change to climate reality is those extremes. And just to really hit on something Raul said, CO2 is a long-lived gas. If we turned off all CO2 production today, it takes, it's like 60 or something years to come out of the system to be sequestrated back into our soils and into our oceans. But you know what? Best time to plant a tree was 10 years ago. Second best time is today.
Wow. Wow. Okay. Thank you. Thank you. We've got a lot of work to do. Okay. Yes, we have a question in person.
A bit of a follow-up, on that, and that is, so yes, the consensus seems to be that it's going to end up 1.4 degrees Celsius above pre-industrial levels this year, with one day, I believe, already hit 2.0. Are you confident as a panel and as individuals that we can keep up with this accelerating pace? I mean, 3.0 degrees Celsius, say, in 10 years from now is catastrophic for Chicago, I would imagine. Confidence? Give me hope, please. Thank you.
It's the challenge we are trying to, at the same time, there is a national climate report that came just last week, looking at the US. So the thing is, if you make it mostly a doomsday scenario, people lose hope. It is not that. So we want to think about all the positive things we are doing right now, and that can happen. That makes us confident that we can solve the problem. If you look at from our side, if you look at things like wind energy, we thought we knew it was useful. It was great, but the way it caught on is amazing. Now the cost of wind energy is cheaper than coal in most of the places. The solar energy is just dirt cheap if you can produce solar. It's just incredible. The things have changed so much because of the scientific advancements we are making. Electric cars, nobody thought they will take off like they did last year. And it's all over the place. Everybody's using electric cars. So the technology is progressing at a quick pace, but it doesn't mean that we cannot do more. For example, for a lot of the industrial sector, agricultural sector, there is very little activity. Can we work more on that? Can we reduce the use of fossil fuels? And one of them is reducing the production of fossil fuels so that the use decreases. So that's one of the things that people are trying to do. So we have hope. It doesn't mean that by 2030, if you don't go to net zero, we all will collapse. But it's 2030 is a nice deadline that people want to do. And 2 degrees is the reason people talk about thresholds is that it is an easy way to connect with population and saying if you cross 2 degrees, these are all the consequences. If you cross 3 degrees, these are all the consequences. It is a communication to the lay people about how these things are changing as things change. Instead of saying at the end of the century, these are all the consequences. Nobody cares. I'm dead by the 20, right? So that's why the conversation changed to this degree changes so that it becomes more personal and immediate to a lot of people.
Yeah, Max, go ahead.
Kind of looping back into the CROCUS scale, which is we have to think about the global scale catastrophe. So I'm going to put that aside for a second. But also mention if you take a neighborhood that's 1 degree hotter than the neighborhood next to it, it's hotter because of decisions that were made over the last few decades in terms of how that land was used. Industrialization, lack of tree cover, lack of permeable surfaces. What would it take to reduce the temperature in that one neighborhood, in that 1 square mile? That is also an important problem in terms of the impact that would have on that community and the people living there. So I do think, I don't want to disregard the need to think about this globally, but there's also large impacts that feel and actually are more tractable at the local scale through the way lands are managed and landscapes in the city are treated. So there's hope in there and there's possibility in there to make real impacts.
Got a question. I'm going to keep it in the back of my mind because many of our audience are from not from the city. I think I'm right about that, right? Many of you are from the suburbs. And so the connection between what's going on in the city and what's going on in the suburbs. Think about that. I'm coming back to you on that. Go right ahead. Question from the audience.
Yes, well, kind of expanding on that, I think my question is really are you going to be able to apply the findings from the Chicago studies to other urban areas around the country or the world? And the second part of my question is, you mentioned the COP conference. Is this going to be discussed at all at the COP conference?
Great questions. Who wants to take the first one about how the work being done in the city, connecting it to the region, the collar counties? Go ahead.
I can quickly take it. So one of the really nice things about CROCUS is there's two things that really make it broadly applicable. One, we're a very open science project. A lot of what we're doing in CROCUS is actually about documenting how we do it. We're also one of 4 urban integrated field labs, the other ones being in Baltimore, Texas, and Arizona as well. And as we've kind of discussed here, we're also really focused on going down to physics, right? Really going down to the fundamental science of cities and urban climate change to try and find results that are what we call generalizable. And by looking at generalizable science, you should be able to take that, the new module that's developed in the model, for instance, and then use it in Barcelona. And we're also part of a global community as well. There is actually a global urban climate science community where we actually discuss a lot of the results that have come up and then look at rerunning our simulations over other cities, because some of those differences are actually really, really interesting. Another really good example there is Singapore. A lot of the things we're doing in Chicago will not work in Singapore because it's so darn humid that planting extra gardens really actually does not lower the temperature of the city. But again, that's why we really get to the fundamentals and we look at the physics of how things are done, and we show our working by being an open science consortium. So the census system you saw out there, we put all the information about how we put that together online so people are able to reproduce our science all around the world.
What about the COP question? Anybody want to?
First decision made at the COP, like today or yesterday, I think, is to figure out a way to fund countries that cannot afford the changes that are happening in climate. So there is the idea of environment, whatever you want to call it, environmental justice, climate justice, is one of the top priorities of this current COP. And there will be lots of discussions, lots of protests, and lots of, it is Dubai, so maybe there won't be protests, but there will be lots of activity on this front there.
Much for that. Okay, yes, online.
Next question is from Hemant from CROCUS. IBM and NASA are building an AI foundation model for weather and climate. Does CROCUS have any collaboration with IBM or NASA for this research? I'm going to sneak in another question from Robyn. What's the expected completion date of the digital twin?
The foundational model. So that's one of the, Argonne is one of the premier artificial intelligence labs in the country because of the computers we have. And we already have a foundational model for weather, which works better than the one the IBM put out. So we haven't written that up yet, but we have one already. So we are working really hard on that, and we will be doing that. For the digital twin, the path to digital twin is through machine learning. You cannot use a physics-based model to do very quick scenario analysis. So we have to develop a machine learning version of the physics model to do the digital twin. So we are in the process of refining our physics model. Maybe in a year and a half, 2 years, we should be started testing some versions of the digital twin.
Thank you. All right. In person.
Good evening. My name is Latanzia Sanders, and I believe I represent a minority here. I am non-technical. I can barely spell IT and AI and all of the other things mentioned here today. So with that being said, what strides are we collectively doing to involve the community more? I think that this is integral, that they have access to this information, but I think for those like myself who kind of understand like the perimeter of everything, but not the nuts and bolts, it's not always, to your point, Rao, personal enough. How do we involve the community so that we can make bigger strides together?
Rao, why don't you, not Rao, Ralph, why don't you take that?
Yes, I can I can certainly tell you that this is a major question within CROCUS. So how do we do it? Let's just take up the last point that you made about the personal. I too think that that's absolutely important. So one of the things, I think this is true for Nidra as well, but certainly one of the things for us in Humboldt Park is to have constant meetings in which the scientists are coming over and discussions are kind of moving ahead. As a matter of fact, I'll have to say this, tomorrow afternoon over Zoom, Max and I, along with the climate committee that represents the Puerto Rican agenda, will be having a meeting over Zoom talking about the plans for this coming year. So those personal meetings are important. There's also a kind of a need for larger meetings as well. So one of the things that I'm kind of very, very excited about is having this group come to a significant meeting. We hold them on a monthly basis in the Puerto Rican agenda. And we'll actually perhaps be talking about the data that we saw earlier. And I can tell you that will generate 1,000 questions within that meeting. Simultaneously, and this is a little outside the scope of CROCUS, but the Puerto Rican agenda, as you can imagine, is very, very interested in Puerto Rico itself. And particularly after Hurricane Maria. And Rao over there has maps on climate change models that are being predicted for the island. And so we're having discussions around that too. And I'm looking incredibly forward to having a local discussion around Humboldt Park and how climate change may be affecting Humboldt Park, let's say 10 years from now, 15 years from now, et cetera, alongside a discussion with regards to Puerto Rico, because the people are constantly moving back and forth. And so if similar situations are occurring in one place and in the other, then that's making a very broad statement to people who might not otherwise put all of the bits and pieces together, but making a very broad statement about how this is impacting at a global level.
Thank you.
I hope
it does, and it sounds like we're due for some TikToks to make this more appealing to the folks that aren't in the room today, but I appreciate you all. Thank you.
Thank you so much, Latanzia. We really have time for one last question, and actually, this gentleman had his hand up first. I'm sorry, but listen, please know that although we want to get to all these questions, we are going to make sure that you are able to get answers to your questions by asking you to submit your question to outloud@anl.gov. And we will respond to every question that's provided in that inbox, okay? So please, I'm so sorry about that. Go right ahead.
Yeah, so thank you for giving me the final question.
Yeah.
So I just wanted to ask, do you have a specific timeline on the CROCUS agenda? What do you expect to fulfill in the next few years? What's your timeline? And is there a specific thing that daily people can do to enhance that agenda?
So I don't know if everyone could hear the question, two questions. What is the timeline for the CROCUS research? And also, what can individuals do to contribute to addressing the climate change issues? How about you, Max? You were shaking your head. You want to take that?
Happy to. So it's a 5-year project. We're about a year into it. So that's 20% in. We have benchmarks along the way, obviously, as you would for the project at the scale, deploying sensors across the city to detect real-time change, building modeling capacities up. So it's a piecemeal process. At this stage, I would say we're in a building phase, and then the next stage will be a discovery phase, in years 3 and 4, and then I think we'll eventually get to the point of the what's next stage. What do we need to build further onto this? So I hope that gives you a little bit of a sense of the scale.
I'll take the second part of that question where you asked, what can everyone do to help? And there's a variety of things. One, if you're going into a community college or into a university, we're always looking for interns as well, so keep your eye out there. And if you just Google CROCUS, you'll find out information about that. We're going to have a series of field campaigns starting next year. We're going to have 4 field campaigns in total, and there'll be a citizen science component to that. We're going to be looking for communities to host small consumer-grade weather stations, handheld meters, even doing things as simple as going outside during our field campaigns and taking a photo of the sky. Or we actually we have community partners working on apps, for instance, to report bad smells, so we can link them to air quality or how hot they feel and things like that. So we have an active, community-driven science component that people can hook into as well.
Thank you so much. Great questions, really, really great questions that added to the discussion in a robust way. We thank you so much. Again, we apologize that we can't get to every question, but we will get to your question if you email us at outloud@anl.gov. Now, before we close, we want to take a moment to highlight some of the CROCUS scientists who are very much involved in advancing the work, but who are not on the stage this evening. I direct your attention to faces of CROCUS.
One word I would use to describe CROCUS is comprehensive.
Innovative, exhilarating.
I would describe CROCUS with the word collaborative.
Collaborative.
Encouraging.
Community.
Community.
People. I'm developing a computer simulation model that includes people and communities and the clean energy decisions that they make.
Looking at building computer simulations where we're trying to look at the interactions between the land and the atmosphere.
I do all of the instrumentation testing, calibration, the tower, all of the tripods that you'll see out in the city I've designed.
Whether they be weather transmitters or air quality transmitters, incorporating these sensors into the Waggle sensor nodes
to understand how land is interacting with the urban atmosphere and how that is changing with climate change.
So that we could improve our capability to predict the climate in these urban areas.
Making sure we get the best observations possible wherever we need them.
And helping people understand all the incredible data that we're collecting as a part of the CROCUS project.
In order to best advise solutions.
The long-term impact I'm hoping CROCUS has is a profound street-level data set of precipitation and precipitation type across the city.
Improve the models that go down to street scale and the neighborhood scale.
To come up with a mitigation strategy, which we can provide to the communities to help combat the climate change.
And we need to give the communities an active role in that science so they can feel empowered.
In order to help them improve our climate for our future. And to positively affect the environment.
Also to get people interested in the weather, to help them be ready for what is next.
And that there's some long-lasting science and community impacts from the project.
Is there a blooper reel?
Nature of CROCUS, and that collaborative nature is really a vital part of the project. So we thank the many researchers. I'm looking at some of the researchers right now, even in the room. We thank you so much for supporting CROCUS in the way that you do. We also thank all of our panelists and our laboratory director for their contributions tonight. It was a great discussion. I'd like to express gratitude also to Jen Nimke and the Office of Community Engagement team, along with our communications team for producing this out loud. And finally, we want to thank all of you for joining us. We hope you enjoyed the discussion. We hope you learned a little something. And we hope you'll join us for our next installation of the Out Loud Lecture Series, which will take place early next year. So have a safe trip home, a great rest of the week, and a happy holiday season. Good night.